Hello and welcome to Empowered Learning. This video will be about decision analysis. If you're taking a data-driven decision-making course or a course where you're trying to make decisions by using Microsoft Excel and other tools, then this video is for you. So first thing that we want to do is lay out what actually goes into what we call decision analysis. And then after that, we're going to, of course, go over several examples, set up some situations or some cases so that we can study these concepts and principles. So in general, we want to learn these objectives. So the first thing that we want to do is identify our decision making environments. And so we're going to see that there are several. And so after we do that, we want to come up with some strategies for making decisions under what we call uncertainty as well as risk. And so what we have done up to now, if you've been taking a data-driven decision-making course, is you've studied situations where you are under in an environment of certainty. But now we're going to see what uncertainty looks like as well as risk looks like. And we're going to properly define what we mean when we say uncertainty and risk. We also want to see how Microsoft Excel is used to solve problems involving decision tables. And so after we come up with our various ways of making a decision on whether we should or should not do something, we'll see how we can set up Excel to be able to run these various strategies to see, based upon what we think is the best approach, what decision we should make. Then after that, we're going to see how to develop as well as accurately use decision trees. And so decision trees are nothing more but trees that we use for networks. Okay, so it's very similar to creating a network. It's just that we're trying to see how everything is connected. So moving on here, we'll also use a feature within Microsoft Excel called Tree Plan to be able to set up and analyze a decision tree. And so the purpose of using Tree Plan or creating a decision tree is that we're limited in how we do linear programming in Excel, because all that linear programming does in most cases when we set things up, it just gives us one answer to one case, one situation. But if we have to make a decision based upon multiple things that we need to consider, then how we would actually do that is after we get one answer from a decision or one result, if we were doing it just the linear programming way, we would have to take all that information, build a new model with the new information that we have, and run a whole nother model to see what answers they are. And so you can see that could get real tedious real quick. So by us being able to form decision trees, and of course being able to do that in Tree Plan, we see how we can do multi-stage decision-making models all at the same time. So after that, we'll also talk about revising probability estimates using what's called Bayesian analysis. So in the presentation, we will be briefly going over Bayesian analysis, and essentially what we're going to do is kind of build you up from the basics of probability to get to a point to where you understand what conditional probability is, and we'll find a real easy way to interpret Bayes' theorem. And then the last thing that we want to do is talk about utility theory. And so what utility theory is a systematic quantitative way of measuring risk. And so we'll see for a given situation of how we can come up with a utility function to be able to model our risk. And so with that, let's go ahead and get started. So the first thing we see here is that in decision analysis, it's an analytic and a systematic approach to the study of decision making. Of course, we base it on logic. We want to consider all the possible options, alternatives that we have, and is going to examine all the available information about the future. And so, of course, in our decision modeling, this is part of the process, because normally whenever we have a decision to make, it's normally not just, all right, we have one set of parameters that we need to look at. It's usually several. And they are also probably conditional based upon one set of things that you do. You'll have certain outcomes, and then you have to make another decision based on that. So all this sort of fits within what it is that we're trying to do here. So the 5 steps for decision modeling, okay? We clearly define what our problem is, of course, list all possible alternatives, identify all future outcomes, and then we need to identify the payoff or the reward, as we could look at it that way as well. We want to identify the reward for each alternative and outcome combination. And then, of course, we want to use decision modeling techniques to choose an alternative. And of course, that also depends upon the approach that you think is best for a particular situation. And so we'll see here in just a second that there's several ways to look at that. So we have this example here of a company called Thompson's Lumber. And so, of course, this is a lumber business. And the situation that we're trying to set up here is this lumber business realizes that, hey, there could be an opportunity in selling backyard storage sheds. And so the reason why they want to do this is because they know that they supply lumber for most of their customers that actually make these particular sheds. And so they're like, well, hey, if we could make the same sheds and make them cheaper, since, of course, we could sell them cheaper because, of course, we're supplying a lot of the supplies to make these sheds in the first place, then maybe we could at least get gain market share in that market, or even corner the market, okay? And so in looking at this, we want to figure out for this company, should they build a large plant to make these backyard storage sheds, a small plant, or just do nothing, and whatever revenue streams they currently have, they just say it's just better for us just to stick with what we currently do. And so, of course, for the outcomes, if they actually built these plants, whether it's a large one, small one, or they do nothing at all, they would either have high demand, moderate demand, or low demand. And of course, for that particular industry, you would get into the particulars about what high, moderate, and low demand would actually mean. For the purposes of this problem, we don't need to go into that deep of a dive to talk about that, but just know that we have 3 outcomes: high, moderate, and low demand. So here's our payoff table. So based upon information given to the owner of JT Lumber, and just knowing his knowledge of that particular market as a supplier, we have come up with a decision table, okay? And so this decision table basically outlines the payoffs based upon the alternative and the resulting outcome. So for instance, if we build a large plant, then if we have high demand, then the expected net profits from building it within a particular time period would be $200,000. Moderate demand would be $100,000. And of course, if we had low demand and we built a large plant, then of course we actually will be losing $120,000. And so of course, if we build a small plant, same thing. High demand, net profits will be 90, moderate would be 50, and for low demand, we would lose 20,000. Of course, for no plant, if we spend no money, we get no reward. So now with step 5, we want to select and apply a decision analysis model. And so here's where we actually go into trying to figure out, well, what approach do we want to take in actually looking at how we should do this. All right, so your decision-making environments. So we have 3 different types. So we have making decisions under certainty. And so if you've been following along in the videos for this course up to this point, you'll notice that everything that we've done up to this point has pretty much been making decisions under certainty. So we won't go into much detail with that because we've done that for several of these videos. Now, for a type 2 would be making decisions under uncertainty and then making decisions under risk. Okay. So to make sure that we sort of cap back from the beginning of this particular course to kind of bring this all together, if you remember, we first said that we were going to have what's called deterministic type outcomes and probabilistic outcomes. And so whenever we have doing things in a deterministic type of way, then that means we know everything. And so that's basically what type 1 is. For type 2 and type 3, they fall under the probabilistic sort of models where we don't necessarily know everything, or we know nothing at all, and we need to still make a decision. So when we have a type 2, which is decision making under uncertainty, we have no information about the various outcomes. And we also have no information on the probability of an outcome as well. So we're kind of going in there kind of blind. If we look at type 3, then we have some knowledge about the probability of each decision alternative. And in this environment, we know that the goal is to identify the decision alternatives that optimizes an expected payoff. So in other words, we want to maximize the amount of reward we get for the amount of risk we go into the game with, so to speak. Okay. And so for what we're going to focus on here is type 2 and type 3 for most of this presentation. So core certainty, every alternative is known, usually one outcome for each alternative, and of course this seldom occurs in reality. And so for uncertainty, we know that the probabilities of possible outcomes are not known at all. And so we have all these particular decision-making methods. And so this is what we're going to focus on here for the next few minutes. So we have what's called a maxi-max, maxi-min, criterion of realism, also called Hurwicz, the Hurwicz model, as well as the equal likely outcome, also called the Laplace model, and the min-max regret. Or put another way, we're trying to minimize the maximum opportunity loss that we may encounter by going with a particular decision. So let's first talk about the maxi-max criterion. So the maxi-max criterion says that we want to maximize our maximum payoff over all alternatives. And so basically this is, hey, what is the best outcome? I'm going to go with that. You know, regardless of what I think may or may not happen, if I know I can get the highest reward going this particular way, that's what I'm going with. And so if we look at our payoff table here, we see that to build a large plant and actually have high demand would be the choice that we would want to go with. So of course we would have to build the plant first, and then we would have to wait to see, do we actually get the high demand? But if you are optimistic, then this is the particular decision that you would make. So if we look at the max-min criterion, then this is the exact opposite of that. So, and that's why this is called the pessimistic criterion. And so here we're just saying, hey, we want to maximize the minimum payoff for all alternatives. And so if we see here, if we look under low demand basically is going to give us an idea of the minimum payoffs. And of course, if we build no plant, we lose no money. So that would be the minimum for this case, because of course for the other two, you're actually losing money. So you're putting money into it and you don't get your money out. Whereas with the no plant, no risk, no reward, as they say. Okay. So now if we look at the criterion of realism sort of model, then basically what we want to do is do a weighted average. And so this will start off by just a qualitative judgment on based upon what the owner would know about that market and past experience in it, to kind of judge, hey, well, what is the percentage of chances that I think everything would go well? And so for this particular example, if we say that the owner said, all right, well, we think it's about 45% chance everything will go well, then we use that as sort of a way to calculate what our realism payoff for an alternative would be. And so we use the Thompson's coefficient of realism, which is basically our guess as to how well we think everything is. We put that in raw decimal form, or probability form, as we say. And then we use this formula here, which is the realism payoff for an alternative. So if you see, we're using our probability that we think things will go well, and that'll be multiplied times the maximum payoff for a particular alternative. Okay, and then after that, we add that to, and now we have 1 minus alpha. And of course, if alpha is 0.45, then 1 minus that is 0.55. So basically what we're saying in that case is this is the likelihood or the chances that we think things will not go well. And so we'll multiply that times the minimum payoff for a particular alternative. So to demonstrate to you how this works, we'll actually do one of these calculations so you see how we come up with these numbers. So let's take this number here, the 29,500. So how we would do that is, of course, we would take our coefficient of realism, which is 0.45, and we would multiply that times the maximum payoff for that particular alternative. And so this number goes with the small plant alternative. So 90,000 would be the highest payoff. So we would say 90,000 here, and then we'll add to that 1 minus 0.45, and of course 1 minus 0.45 is going to be 0.55. Okay, so here we would have 0.55, and that will be multiplied times the minimum payoff for the alternative. And of course, the minimum payoff here would be if we had low demand. We would actually lose $20,000. And of course, from there, if we went ahead and multiplied 0.45 times 90,000, we would get 40,500. I'll go ahead and write that. And then, of course, if we do 0.55 times a negative 20,000, we would get negative 11,000. So that would be minus 11,000. And of course, the difference in between all of that should come out to be your 29,500. And so that's how we do that calculation. And if you notice, we did this by hand, but if we were to automate this, we could actually do it in Excel and do one calculation and then just copy and paste and get all the others to follow suit. So the equal likely or Laplace criterion just does an average. So basically what we're doing here is for each alternative, we're adding up all of the outcome payoff values and then dividing it by the number of payoff outcomes we have. So just to kind of explain here, let's say we go with a large plant. So with the large plant, we would basically do 200,000 plus 100,000, and then that would be minus the 120,000. And then of course we divide all that by 3. And if we do that, then you'll see that we end up getting $60,000 when that happens. So next we want to talk about what's called the min-max regret criterion. So when we talk about regret, regret is another way of saying opportunity loss. And so how we actually calculate what opportunity loss is, it'll be the optimum or the highest payoff for any particular outcome. So we'll say high payoff of an outcome. And we're going to take that and we're going to subtract that from the actual payoff for an alternative. We're going to say actual payoff for alternative. Okay, and so we'll do some calculations here just to make sure that all of this is clear. So if we look here, we're actually doing the calculations to start off with. So let's go back a slide to try to see how this particular table is formulated. So we know that in order to calculate opportunity loss or regret, then we have to first pick the optimal or highest payoff for a particular outcome. So our outcomes are high demand, moderate demand, low demand. And so for high demand, of course, the highest payoff is 200,000. And then and also we have for the small plant here will be 90,000, no plant is that. So for high demand, it ends up being 200,000, okay? Now for the moderate demand, it will be 100,000. And for the low demand, the highest payoff would be 0 here. So for the high demand, moderate demand, and low demand, we're going to use 200,000, 100,000, and 0 respectively. So how we come up with what the min-max regret criterion would be here is we're going to take this 200,000 and we're going to subtract that from every number that's in the high demand column. So we're going to do this 3 times. So the first time we do it with what we get whenever we have a large plant, so what our net profits will be. And so that is what the actual payoff received for a particular alternative will be. So that's what I'm talking about here in this second part, what we're subtracting away. So the actual payoff for the large plant alternative is 200,000. And of course, that result ends up being 0 when we do it. If we do the same thing for the next alternative, which is the 90,000, then of course there, if we take 200,000, subtract 90,000, we end up with 110,000. And then of course for the last one, if we have 0, then the total result is 200,000. Now, what this actually means is this. When we are calculating the opportunity loss, what we're saying is that, hey, if we pick that opportunity, this is how much money we're going to miss out on making based upon the outcome and alternative mix. Okay. So here, what we're saying, and I will just talk about this first one here, and actually I'll go back to this slide. So here what we're saying is that, hey, if we build a large plant and it actually ends up being high demand, we're missing out on no money. So we've made all the money we could possibly make in making that decision. If we build a small plant and it ends up being high demand, then there's a potential of $110,000 that we did not make because we built a small plant instead of a large plant. And of course, if we build no plant, then we spent no money, so there was no way for us to even have a chance to earn this $200,000 in potential net profits that we could get. Okay, and so that's how this works. Of course, The same exact thing works for the moderate demand and the low demand. And so I'll go ahead and go to the low demand and calculate that just so that you have another example of seeing this. All right, so I'm going to go ahead and erase this stuff down bottom right quick, and we're going to work all this out again. All right, so for the low demand, we see that the largest payout here is going to be 0, meaning that we do not lose any money in this case. So here we would have 0 minus, 0 minus, and 0 minus. And so now what we do is say 0 minus what? So we're going to look at each alternative, see what its payoff is, and use that. So for this first one here, we see that we could lose $120,000. So here, since we know that subtract a negative is the same as addition, this is actually like adding. And so here we miss out on a potential $120,000 if we don't build a plant, and indeed we see that it ends up being low demand. So for the next one, we stand to lose $20,000 if we actually build it. But we see here the opportunity loss or regret is $20,000. So there's a potential $20,000 that we may lose if indeed we build a small plant and there is no demand. And then of course for the last one, if we build no plant, then of course we lose nothing. Okay, so that's how that works. And so you see we get the same exact thing here. All right, so now that we've done the calculations for that, let's see how to actually complete the min-max regret criterion steps. So we go to our next slide here. If you notice, we have a column here for high demand, moderate demand, and low demand, just like how we had before. But now our numbers have changed. And so if you see, in the high demand column, we have 0, 110,000, and 200,000. And so these are the same exact numbers that were here. So what we've done is we've figured out what is going to be our maximum number, what is going to be our regret, rather, based upon the outcome alternative mix. Okay, so under high demand, we figured out what is our regret if we build a large plant, small plant, or no plant. So we want to list all that information. So all these numbers go into the high demand column, these numbers go into the moderate demand column, and these numbers will go into the low demand column. So once you see that, then to finish this out, what we want to do is for each alternative, we want to see what is the largest amount for each alternative. And so you see in this first row here, for the large plant, we have 0, 0, and 120. So of course 120 works. Okay, so we see that if we build a large plant, what that means is the maximum amount of regret that we will have, or the maximum amount of money that we're going to miss out on, is going to be 120,000. Okay, if we decide to build a small plant, then we see from our regret or opportunity loss calculations, we see that we had 110,000, 50,000, and 20,000. So if we made the decision of building a small plant and we had high demand, the most that we stand to lose in missed out net profits is going to be 110,000. So that makes it to this extra column here. And then of course, if we build no plant, then of course, and we ended up having high demand, then we're missing out on being able to make $200,000 in net profits. So of course that makes it here. And so now our goal here is, since we want to make sure that we are minimizing the maximum amount of opportunity loss that we would have, we would just pick the smallest number out of this column. And so that is why 110,000 would be the answer for this. So basically what we're saying is if we wanted to minimize the maximum amount of money that we may not potentially make, then we would have to go with building a small plant. And of course, the hope is that if you built that small plant and you had high demand, you would lose out on making money, but the amount of which you would lose out on making money would be the smallest. So it's sort of taking a sub-pessimistic kind of approach, okay? So now this is what it would look like if we were going to employ all of these different type of strategies to try to come up with a decision on what we should do. And if you notice here, I have all this in Excel. My yellow cells here are the actual decision variable cells, or the numbers that I'm trying to solve for. This cell here is what the coefficient of realism would be for whoever or whatever institution is looking at this. And then of course the rest of these cells here are how we come up with how we program everything to come up with the various outcomes here. So what I'm going to do is zoom in on this so that you can see what these formulas are a little bit better, so that if you want to sort of mimic this and what it is that you're trying to do, you can have a chance to do that. So I'm going to go ahead and make this bigger first. So the first thing I want to do is concentrate on, I guess since I have this near me here, the regret payoffs, or the opportunity loss payoffs. So this is how you would actually come in and program all of this. And so, of course, for here, this is basing everything off of B5, B6, and B7, which are your high demand values here. Okay. And of course, for moderate demand, be C5, C6, and C7. And for low demand, D5, D6, D7. And of course, the max amount that you see here is the max amount out of all of these cells from B5 to B7. So remember how we said we need to take the maximum payoff for each outcome. So how we program that is to do the max of these three cells here, B5, B6, B7, okay? And so that's how that works. So moving on over, I'm going to scroll up. Our max criterion, we want to maximize a maximum payoff. Of course, we see the max in between B5 to D5. And so B5 to D5 would be just all of these yellow cells up here. And of course, if we were going to make that choice for the max and max, then of course we'll do some if statements here. And for E5, says if E5 is equal to the maximum of all the cells from E5 to E7, then we're going to put the word best by there. Otherwise, if you see the parentheses there, we put nothing, or nothing will show up there. And of course, same kind of thing goes through for the Hurwicz. Of course, the way that we calculate the actual realism payoff is different. The F14 here, that's the coefficient of realism, and we do that with the maximum payoff out of B11 and D11. So if we look here for B11 and D11, here are those particular outcomes that we talked about earlier. And then of course we add that, do 1 minus this times the minimum payoff for B11 through D11. Okay, so that's the smallest amount out of all of this. Of course, for the min max regret. We want to maximize the minimum regret or the minimum amount of opportunity loss we can experience. So sort of the same thing. You can just kind of copy this and it will come out to be what you need it to be, provided that you set up everything the way you need to here. And of course, the maxi-min choice here, we want to minimize maximum amount. And of course, for the equal likely, we're just taking the average of those particular payoffs. So again, I'll go ahead and get this back in this view here at 80% so you can see it. And of course, for each one of those cells, you can just model your Excel file like this one, and you should come out with those same answers after you run the Excel solve. All right, so now if we run all that, and we'll see if we sort of minimize or get rid of those particular cells that actually do the calculations, and we just show what the outcomes are for each of those different decision models or decision model strategies. Then you'll see that the word best is located by the best choice based upon that approach to make the decision. Okay. So you can see based upon what we feel or what approach we take, sometimes we get a different answer based upon it. All right, so now what we need to do is talk about making decisions under risk. And so when we make decisions under risk, one of the things that we try to do is sort of calculate what's called an expected value for taking that risk. This is a term that's popularly used in probability, and you can use it from anything from gambling, lotto, to actually making a business decision on whether to invest in a particular venture or not. And so the expected monetary value is just basically you take the payoff of the first outcome times the probability of whatever you think that first outcome is going to be. So the probability of it happening. And then you do the same thing with whatever the second outcome is times the probability of the second outcome happening, and so on and so forth. Okay. So if we keep on going here, you'll see if we take the approach of an expected monetary value, then we have all the payoff values here. And then if we do the expected payoff, then we see that all this is linked to these probabilities here. And so where these probabilities come from are our owner for the lumber company. And he's saying, okay, well, I think there will be about a 30% chance for high demand if we were to actually make these backyard storage sheds. There's about a 50% chance that we're going to have moderate demand, and about a 20% chance we will have low demand. So we take that qualitative insertion of data for that the owner's given us, and we use that into our calculations here. And so we see that essentially all we're doing is we are taking this amount, multiplying it times probability. This amount, multiplying it times probability. This amount, multiplying it times probability, and then we add all those answers together. And so we do the same thing with small plant and no plant. We get these following numbers as the expected value. And so we see here, using that particular strategy, we would want to build a large plant, because basically we're saying that if we invest the money into building a large plant, we can expect to see on average about $86,000 in net profit. Okay. Of course, not as much as when we looked at, let's say, our min max regret, because in that case, we're saying, all right, how much we stand to lose. But we're sort of looking at it as an approach of, all right, on average, you may get a little more here, get a little less there at times, but on average, you're going to get about 86,000. And so, of course, if for me being the owner of this business, if I was the owner of it, I would have to set a certain threshold as to what I think is acceptable and what is not for the type of business I'm about to go into, or the new business I'm about to create under my current business. Okay. All right. So next, we could also calculate what's called the expected opportunity loss. So instead of saying on average how much we're going to gain, we could also look at it as, all right, well, on average, how much do we stand to lose? And so, of course, if we're looking at things in terms of how much we stand to lose, we want to minimize that amount. So that is why the minimum expected opportunity loss should be the same as the maximum expected monetary value. Okay. So in other words, if we're using those numbers to make our decision, whatever number ends up being the minimum expected opportunity loss should map you to the same decision as it would be if you were trying to maximize the expected monetary value. And the way we calculate this is very similar. So instead of looking at the payouts, we look at the regret. And so, of course, that table that we were looking at when we talked about the regrets or the opportunity loss, we would use that instead of the other table that had the payoffs. And I'm going to go back some slides so that you can actually understand where I'm coming from here. So here is the actual payoff table here. Of course, I have a lot on it now since we've been writing on it, but here are the actual payoff tables here. And so that's why when we saw, get to it, this table here, it looks very much like that one we just got through seeing. The only thing that's different now is we have the probabilities. Now, when we go look at the regret or opportunity loss, what we will be looking at is this table. So after we come here and calculate all of these values that we see here, then we put them in this corresponding table. And then if we had the same probabilities of 0.3 for high demand, 0.5 for moderate demand, and 0.2 for low demand, we would do the same kind of thing and just multiply the regret value with the probability plus next regret value with the probability plus the low demand regret value with the probability. So when we go back here, that's exactly what we should see. So again, that is doing the expected monetary value. So here you can see for high demand, moderate demand, and low demand, these are indeed the values of the regret or opportunity loss for each outcome. And so here we would have 0 times 0.3, 0 times 0.5, 0 times 0.2. Okay. So we see here that makes sense, $24,000, because 20% of 120,000 is $24,000, and we get 0 everywhere else. And so our goal here is to pick the smallest number out of this. Of course, if we kept on multiplying here, here, and here and adding, and then the same thing for the no plant option, then we would see that 24,000 is the smallest number. So to build a large plant would still need to be the decision. And it's the same decision as making it if you were using the expected monetary value. Okay. So now that we know this information as far as being able to use our payoff values to make decisions, one of the things that we want to look at is, well, before we make this decision, is there any information I can find out to help me in making my decision. As of now, all we've been doing is using probabilities, and really this is just a guesstimate by the owner. Okay, but what if we wanted to actually go to a third-party vendor or third-party source to be able to get some information about this new market that we're going to go into before we make our decision, because we want the data that we could possibly get to help us out in the decision-making process. Well, the next things that or next concepts that we're going to study is going to address exactly that. So the first particular concept that we need to make sure that we understand is what's called the expected value with perfect information. Okay? And so what this basically represents is the expected payoff if we know everything that we need to about this market before we actually make our decision. So basically we had the oracle come down and say, hey, this is exactly what's going to happen if you do this. How much should we pay the oracle? So to put it in those terms. And so how we would calculate that is we basically take what is the probability of the first outcome, and we're going to multiply that by the best payoff for the first outcome. And of course, the outcomes are high demand, moderate demand, low demand. So when we look at this, we're saying, all right, so best payoff for high demand, and then probability of high demand. And then the second would be moderate demand times the probability that moderate demand will happen, and then payoff for low demand. Okay. And so now we figure out what is called the expected value of perfect information. Okay. And so this basically tells us at most how much we should be paying for this perfect information if we could have it. Okay. And so what we mean by perfect information is, let's say that we have a particular firm or institution that has been recording everything there is to know about the backyard storage shed industry from its infancy. And so they have all this data compiled and together. And of course, if people want this particular data, they have to pay for it. And so what we're trying to figure out is, with the expected value of perfect information, how much should we actually pay for that knowledge, or for that research, rather. Okay. Now, if we go back here, when we talk about the expected value with perfect information, what that is how much we can expect to get on average if we had that perfect information. Okay. So just want to make sure that we make that clarification. Expected value with perfect information is, on average, how much can we expect to get in our pocket, so to speak, in net profits in this example, if we had that information. Here, when we talk about expected value of perfect information, we're trying to figure out how much should I actually pay for. Okay. And so we see here that the expected value of perfect information ends up being the exact same amount as the minimum value for expected opportunity loss. Okay. So whatever the minimum expected opportunity loss is, that should be how much in general you should pay for that perfect information. Okay. So now that we know the difference in between expected value with perfect information and expected value of perfect information, let's fill in some more details about this example of JT Lumber's company and their whole decision-making process and what they're doing to be able to come up with a decision on whether to enter the backyard storage shed business is or not. So let's say they employ some company, and that company's name is Scientific Research. And so they're the ones that have been doing research, documenting research on backyard storage sheds since its infancy. Okay, and let's say they have all this information from all these years. If they charge you $30,000 for this information, according to what we see about the expected value of perfect information, we shouldn't pay that. It's too expensive. And we see that because if we look here, the expected value of perfect information, again, tells us how much we should pay for perfect information. And it should be no more than $24,000 based upon the probabilities that we have here and our payoff amounts. Okay. Now, with the expected value with perfect information, of course, this is telling us how much on average we should expect to get for being able to go into this business, regardless of how we look at it. Okay. And so, of course, this is also the same thing as the minimum expected opportunity loss. Okay. Now, the maximum expected monetary value is on average how much we could expect to get for all three alternatives if we look at the best one. Of course, for the large plant alternative, that actually end up being the best. So that's the maximum amount on average we can expect to get out of all three alternatives. So we're maximizing what we expect we could get, and we're comparing that to, on average, from a low end, what we could expect to lose, and therefore that's how we come up with the $24,000. And if scientific research charges us $30,000, then of course we need to basically say, well, hey, thanks, but no thanks, and try to find another way to come up with some additional information about this market. However, if they decided to go down to $20,000 or maybe even $22,000, then according to what we see here, we should go ahead and just pay that $20,000 or $22,000 for that perfect information. And so on this next slide, again, if you have Excel, this is an example of how you could set up an Excel worksheet with the functions already shown in here to show you how to make these calculations so that you'll know what your maximum expected monetary value would be. In other words, on average, what you can expect to get and in your pockets, and as well as the minimum opportunity loss as well. And that's, of course, same thing as the expected value with perfect information, and trying to compare those two. Okay. So, of course, if we use Excel to come up with this, we'll actually see that we would end up making the same decision, but we would just look at it from different viewpoints. So if we want to maximize the expected monetary value, that's going to be the same as minimizing your expected opportunity loss. Okay. And of course, we also know, in addition to that, this info here, we know how much we should actually pay for perfect information. That tells us that right there, 24,000. So now what we want to do is sort of turn a new leaf and talk about decision trees. And so mainly we use decision trees whenever we have multiple decisions to make within a major decision. So to put it another way, we have decisions that we need to make that are conditional upon other actions or previous decisions that we need to make. Okay. And so we're going to learn the basics about coming up with a decision tree and show you how this looks a lot like a network, and show you how to be able to analyze a decision tree to be able to figure out these multi-stage decision-making processes that we need to do. So if we were to take our situation currently here, which is to say, all right, well, we have a large plant, small plant, no plant, and we also trying to figure out whether we're going to have high, moderate, or low demand, this is how our model would look in a decision tree type model. Okay. So all we've done here is taking our situation that we had when we were looking at our payoff table, and we just put it into this decision tree form. So of course, if we were looking at this going from left to right, in reality, we would have to make a decision upon whether we're going to build a large plant, a small plant, or no plant at all. And then once we made that decision, then what we would have to do is figure out, and of course, we wouldn't know this until we actually build the plant and start a business, is to figure out, are we going to have high demand, are we going to have moderate demand, or low demand? And then of course, the payoffs that you see at the end are the exact same ones that you've seen in the payoff tables earlier. And I'll go back to that payoff table just so that you see it. So what we're going to be looking at here, let's just take these first three payoff values here. These first three payoff values are going to be the same payoff values that we see for the large plant alternative under the high, moderate, and low demand outcomes. And so I'll go back and show you where that is now. So now we're back here at the payoff table, and you see that same numbers that we had, the 200,000, 100,000, and minus 120 are right here in this row. So we've just taken this particular payoff table and we put it in tree or networking form so that we can work with it a little bit. And thus now you can understand why the second group of numbers of 90,000, 50,000, and 120,000 were the same numbers that were in the payoff table going from left to right for the build small plant alternative column. And of course, for the no plant, all of them ended up being 0, so that's why we just have this option here. All right, so if we write out everything in terms of how we're looking here, when we analyze this decision tree, how we actually analyze it is to go from right to left, and that's called folding back the leaves on the tree. So when we originally looked at being able to build this, we went from left to right, because of course the first thing we had to do is figure out, are we going to build a large, small, or no plant? And then after that, we had to wait to see, are we going to have high, moderate, or low demand? But if we're trying to analyze this to make sure that we know what we should do, we should actually start from this way and go back. And so, of course, how we get this 86,000 that way is we just do the 200,000 times 0.3 plus 100,000 times 0.5 times negative 120,000 times 0.2. And whenever we get all those numbers there, whatever the highest number is actually ends up being the one that we use. And what I mean by that is for all three of these. Of course, when we take 200,000 times 0.3, 100,000 times 0.5, and negative 120,000 times 0.2, we get $86,000. When we repeat that for the small plant, 90,000 times 0.3, 50,000 times 0.5, negative 120,000 times 0.2, we get the 48,000. And of course, for if we build no plant, we make no money, so we just end up with 0 there. And then of course, if we're making it this way, to make our final decision, what should we do? According to what we see here for the expected payout or the expected monetary value, we see that building a large plant here would be the most advantageous thing for us to do. Okay. And of course, those calculations I was talking about up here are down here as well. And so again, if we were just folding back the tree, the first thing we would do is do these calculations and then come to this point here. And so then once we fold back that, then we say, all right, well, based upon this, what should we do? Make large, small, or no plant. And of course, it makes sense for us to make the large plant using this particular method. Now, if we actually want to use the tree plan in Excel, um, there is a file that you could download um, that you can actually use. And if you're taking this data decision making course with me, in your learning assignments area, you actually have this particular file. So you can download it and then just add it on to Excel as an add-in. So I'm not going to go through the specifics of doing the tree plan here, only because if you're in my course, you also have an Excel file with a lot of examples in it, and you should be able to take that file, and one of those workbooks that's in there actually has the tree plan setup that you're about to see here. So all that I'm going to do here is basically go over the slides so you can see what the features are as you begin to build your tree. And so once you actually get this thing uploaded and going, of course, you would click on this to build a new tree. And you always start off here with your decision node and then terminal nodes here, and which are alternatives. And so if you're going to edit a decision node, meaning you're going to edit the one with the that looks like a square, then these are the instructions for doing that. Okay. Of course, you can always just go to tools and then do decision tree, and then this comes up and you can go ahead and do what you need to do there. If you want to edit a terminal node, and of course that's the ones that look like triangles here, then you could follow these instructions here to do that. And so of course, as you're building the trees or whatnot, you can select the choice there to highlight your decision trees. So again, you just have some other options here. And so let's go ahead and move on. So once you're done building everything, for this particular example that we've been talking about with the JT lumber, this is what it would actually look like. And so if we move forward here, this is what it would look like in Excel once you actually put in all the information. And if you notice, we got our probabilities here. We have our labels for what each of these branches are. And so if we want to see it color coded, this is what it looks like. And so everything that's in yellow is what our probabilities are. So that's where you would type in your probabilities. So that's something that you would have to type in. Also your payoffs. Payoffs, of course, you know what these values are. We have to put that information in as well. And so the labels, of course, labeling what our arcs are going to be is something else that we have to put in. And so everything that is in this light kind of reddish pink color here is what is actually calculated for you once you put everything else that's in the yellow or the green or the light blue there. Okay. So of course this window here, you'll see that this talks about figuring out whether you want to do your certainty equivalence using a utility function or expected value. So later on in this presentation, in part 2 of it, you'll learn more about the utility function and being able to measure or model risk. Whereas right now we're doing more of the expected value. So that's why we have that selected here. And of course, for this case, we're in a situation where we're trying to get into a new business, so we're trying to maximize profits. So that is why we're selecting to maximize profits there. Okay. Now down here, I have these instructions based upon whether you have a PC or a Mac, because sometimes this looks a little different when you go and try to access these tree plan options depending upon what kind of computer you have and what type of programs you have on it. Okay. So now if we take our decision tree skills that we've just learned, and now we look at this example, we could expand this out even further. And so the situation now is, again, we have JT Lumber. JT Lumber wants to get into the backyard storage shed business. The owner sort of has an idea about what chances is going to take for that business to experience high demand, moderate demand, and low demand. Also has a strategy for trying to figure out the expected monetary value and the minimum opportunity loss, so he can figure out exactly how much his business should pay for perfect information. And that's the expected value of perfect information. And we get that, of course, from figuring out the minimum opportunity loss and the maximum expected monetary value payout. Now, we found out that this third-party vendor that has all this information about that industry wanted to charge $30,000 for its information. We found out from doing the expected value of perfect information calculation that we should pay no more than $24,000. So we need to seek some other alternatives. And so now we've run across another firm. And the name of this firm is called Smart Services. Instead of them compiling research data for years and years and years, what they've done is conducted market surveys. So of course, after everything has happened, they have surveyed the people that's in this particular market, and those that participated gave information about it. Of course, hadn't been around nearly as long as the scientific research services. And in addition to that, doesn't have as much information, because as you know, you can field surveys out to a lot of people, but that doesn't necessarily mean that everyone will participate. So we have this situation now, and Smart Services, they want to provide services for us to be able to get surveys done on this market, and they're charging us $4,000 for that information. Okay. Now, of course, from what we see here, we know that we can pay for that because we were willing to pay up to $24,000 for perfect information, right? But the thing is it's kind of the whole thing of you get what you pay for. So you want to figure out, if I spend this $4,000 to get this information, is this going to give me, of course, it's not going to be perfect information, but how much more close do I get to being able to accurately figure out what's going on in my market? And how do I compare that with having the perfect information? Okay, so how much am I off from being able to have that perfect information there? So this is the kind of thing that we're going to study next. So the way that the owner wants to sort of analyze this new situation here is, of course, we want to extend this decision tree. So up until this point, the only thing that we considered for our decision tree was this particular area here. In other words, we do no survey, we work everything out. We've extended this tree now to now also conclude us being able to have a survey. And of course, from that survey, we know we may have positive results, we may have negative results. So if we're trying to take all of this into the mix, then of course our tree expands a lot. And so if you see here, we have all these payoffs here, and we have these different payoffs for the other two options. And so if you notice, all the payoffs that we have for the option of conduct a survey positive results and conduct a survey negative results, is basically we're subtracting $4,000 from each of these outcomes here, okay? And so we're doing that because if we actually conduct a survey, then we're paying $4,000. So that means our cost went up $4,000, which means our net profit is going down by $4,000. So that's why you see all those numbers there in red circled. So now what we want to do is we want to figure out what decision we should make by analyzing this decision tree based upon all the possibilities that we have going on now. So if you notice what I have circled here in the black, we already have done this portion of the decision tree already, okay? And so what we ended up with when we first did this, just to kind of write this in, of course, when we did the expected monetary value to find out the maximum amount for all of this, we had 86K for the case here for this decision node 1, terminal node 1 here. We had about 48,000 here when we did the calculations for that one, and of course we had 0 for this one, and we ended up with $86,000 as being the best choice for that. So we want to do the same exact thing again, but we want to do it with these situations here. And if you notice, the probabilities that we have for high demand, moderate demand, and low demand are actually different here, here, and here. And so we've had to revise what those probabilities are. And we're going to see later on in part 2 how we're actually going to do that, okay? But for now, let's go ahead and figure out for nodes 4, 5, 6, 7, 8, 9, and 10, what corresponding values we need to assign to those. So of course, if we do no market survey, this is just like what we had before when we were in a situation where scientific research, they offered their services for $30,000 and we rejected them. And we said, okay, all right, well, if we just go blind into this situation based off of the only thing is that we have is our owners, which is Mr. Thompson, go off of his probabilities of thinking for high, moderate, and low demand, this is the outcomes that we would have here, okay? And so we've already seen these before. If we go to the next one, which is node 4, node 5, and node 6 here, then the way that we read this is as follows. We say for the expected monetary value for node 4, this is the expected monetary value of building a large plant, given that we know that we're going to have positive results from the survey. And so when we read this sort of notation here comes from conditional probability, okay? So I'll say it again. To find the expected monetary value for node 4, that is the same as saying find the expected monetary value of building a large plant, given that we already know that the results of the survey are going to be positive, okay? And so we notice that when we calculate this, we're going to have the 196,000 times the probability that went with that of 0.509, and we'll go back to show you where that is. So here we're taking this amount times that probability plus the 96,000 times the probability of 0.486, and then the payoff amount of minus $124,000 and multiplying that times the probability of 0.023 or 2.3%. And of course, if we multiply and then add all that together, then we get this number here, the 141,840, okay? And so that would be expected payout monetary value or expected payout that we would receive on average for that particular situation. Doing the same thing with node 5, we get 64,750. Node 6, of course, we just get 4,000. So, and node 6 would be the case of when we say, all right, well, we want to pay for the survey, but we decided to do nothing. And so in that case, we only lost $4,000. All right, so moving on, for nodes 7, 8, and 9, of course, this is dealing with building a large plant, and we have negative results from our survey, small plant having negative results from our survey. And then, of course, again, node 9 is, well, we decided not to build a plant at all. We decided to pay for the survey, but after that, we just decided not to do anything. Then, of course, for node 10. So for node 10 is like our second layer. So I'm actually going to go back so you can see where node 10 is and see why we have these numbers of 87,961 and why we're paying attention to the $86,000 figure again. So here, once we're done, we would see that we would have these numbers here. The highest one that comes from all three here would be here. Highest one coming from the large plant, small plant, no plant will come here. And then, of course, the highest one from all three of these others would come there. And let me see if I can make this look a little better. All right, so you can kind of see what's going on here. We want to try to fill in these numbers. So we have, for node 4, we ended up with 141.8K. And for the next one, we had 64.75K. And for node 6, we ended up with just a negative $4,000. Then if we go to the next ones here, we would have approximately, I think this is 2.82K, have 16.54K, and for node 9 down here, again, we would have minus 4,000. So let's see if, and so now once we make those decisions here, of course, the largest number out of nodes 4, 5, and 6 will be the 141.8K. And the largest one out of nodes 7, 8, and 9 would be the 16.54K. Okay. So then, of course, out of all of that, now we come up with node 10. So node 10 is basically saying, hey, I need to make a decision in between what I have going on here. So now the information that we received whenever we were trying to get information from Smart Services, which is the company that's going to do the survey for us on the market, we see from their past history that whenever they've done this, they have about 57% chance of getting positive results and 43% chance of getting negative results from the survey. So to come up with what node 10 should be, we should just do the 141.8K, which is 141,800 times the 0.57, and then we add to that the 16,540 times the 0.43, and then we come up with our expected monetary value for the survey period. And what that number comes out to be is about $87,961. Okay, so it seems like from that, that will be our expected value. So on average, how much we could expect to get in our pockets in net profit if we went with the survey, about $87,961. Okay. Now, of course, here, our 86,000 that comes from over here is going to slide on down because it has no other competition. And now you see it there. And well, maybe I shouldn't put it here. It's going to come here. Okay. And so now we have to make a decision here. So what should we do? Should we conduct a survey or should we not conduct a survey? Well, we see that our expected monetary value or expected payout that we think we will receive on average is more if we conduct a survey. That's telling us that we should do it. Okay. And so that's why on the slide that we were on, that's why you saw the 87,961. So let's go back to that slide now. All right, so now that we're back to that slide, now you see where this 141,840 comes from times the 0.57, and then the 16,540 times the 0.43 comes from. Because again, this is just probability of having a positive result from the survey. This is probability of having a negative result from the survey. Okay. And we see that because of this, if our results are positive, we should build a large plant. And if our results are negative, we should build a small plant. So that's what it turns out being that we should do. And of course, for the decision that we're talking about here, we could actually go back to our decision tree and actually see where we get that from as well. So let's go back there. So from what we talked about earlier, we definitely know that since this number here is smaller than this one, then we should definitely conduct a survey. But if we have positive results, then we should build a large plant because that was the largest number that we had. Okay. If we went and we found that we had negative results from the survey, then we should build a small plant because that was the largest number that we had there. So that's how we can use our decision tree to not only make a decision on whether we should conduct the survey or not, but we can also see, based upon the outcome of the survey, what we should do. All right, so now I'm going to go back to where we were, and then we'll move on in the presentation. All right, so now that we're back at this slide here, we kind of understand how everything was put together and how we're using the expected monetary value to help us make our decisions on whether to conduct surveys or not, as well as based upon the results of the survey, what kind of plant to build. And so if we put everything together, if it looked all nice and neat, this is what it would look like. And so this is actually what I was forming for you as we went through that example there. So you can just take a moment and look at this just to make sure that everything that you may have down, if you're following along, sort of goes along with what we're saying here. And anytime you see these double marks here, that's just telling you, hey, this is the route that I want to go, based upon the decision-making process here, okay? All right, so now we're in a situation where we need to talk about what's called the expected value of sample information. All right, so when we talk about the expected value of sample information, what we're trying to do is quantify the value of this conducted survey that we're going to do, just like how we use the expected value of perfect information to be able to quantify the information that scientific research was going to give to us that they were trying to sell to us for $30,000. Okay. So in doing that, the first thing that we need to do is make sure that we add back that cost for doing any research to the expected monetary value. So in other words, that $4,000 that we paid for the survey, we need to add that back in to the mix there. Okay. And if we see here the expected value of sample information, and of course we're saying sample because we did a survey, and your survey is basically sampling your market instead of giving you information about all of it. So that's why it's called that. So we find that by doing the expected monetary value of the best decision with the sample information, which we just got through calculating here in the previous slides there. And we're assuming that you did not have to pay anything to get it. So that's why we're adding back the $4,000 in for the survey charges, okay? And so we take that and we subtract from that the expected monetary value of the best decision without any information whatsoever. And of course, that would be the case of if we did not conduct a survey at all. If we just said, all right, we're going with JT Lumber owner's decisions on what he thinks about the market probability-wise of high, low, and moderate demand. And of course, we saw that when we did that, that was the 86,000. So in looking at that, we see that we had the $87,961 that came out from the decision tree. Whenever we were looking at everything, we saw that we should indeed conduct a survey because the expected monetary value for doing that on average, if we conduct a survey, tended to be higher than it would if we did not. But we add back the cost of the survey and then subtract that from the expected monetary value if we wouldn't have did the survey at all. And so we see that the $5,961 is the max amount that we should have paid for the survey in the first place. And of course, we fell well within that, okay? So at $4,000, so we're good. Now, what the efficiency of sample information is basically saying we want to know, well, what portion or how perfect did the information that we have would be compared to getting perfect information, okay? So that's one way to put it. Another way to put it is we know that our information here, once you see the calculations, will be about only 24.84% as good as the best information available. So, you know, roughly about 1/4 as good as the best information that was available, okay? So again, you get what you pay for in some instances, and so you have to sort of balance those things out. So with that being the case, there's a over 75% chance that what we're expecting to happen may not actually happen, but for the amount of money that that we were going to possibly put into it, we kind of balance it out and say, okay, we're willing to take that risk for that, okay? So that's kind of what the efficiency of sample information is all about. So you just take the expected monetary value of sample information and divide that by the expected value of perfect information. All right, so this concludes part 1 of the presentation on decision analysis. I know the video was very long, but again, there's a lot of information that we're trying to cover here. So I'm going to go ahead and start with part 2. And part 2 is going to consist of Bayesian analysis. So we'll see how, and I'll go back to these slides right quick. So we'll see how these numbers that we get right here for the probabilities, how we actually got those numbers and how they actually played a role in our decision making, okay? Because if you remember, when we were talking about making, we're not taking any survey at all, of course, our numbers were a little bit different. Or to put it another way, whenever we were talking about just using the probabilities of the owner, those probabilities were different, okay? And so if we go back here, these, not those, but these probabilities right here are what I'm talking about. We originally had those, but if you see, a lot of these changed. And so when we study Bayesian analysis, we're going to see how we actually, what we actually use to be able to change those to get a more accurate description of the probability of each of those cases there. So that's what we'll do in part 2. Thank you for checking this out.